In this video, we're going to talk more about differential equations, but we're going to talk specifically about what are called separable differential equations. So a separable differential equation, you can think of it as something like this. dy dx is equal to a function of y times a function of x. And what we can do with that is we can multiply both sides by dx. So we'll do that. And then those cancel on the left-hand side. And then we're going to divide both sides by f of y. And we end up with the following. We end up with 1 over f of y dy is equal to g of x dx. And then we can integrate to solve those. So as an example, let's say we have the following. dy dx is equal to x divided by y. We want to get it into the form above. Basically the x's and the dx's on one side and the y's and the dy's on the other side. So what we're going to do is we're going to end up, you could think of it as cross multiplying in this case. We end up with y dy is equal to x dx. And what we have on the left-hand side we can integrate, and on the right-hand side we can integrate, and we have 1/2 y squared is equal to, well, let's do this. Let's say plus c is equal to, we'll call it c1, is equal to 1/2 x squared plus c2. And to make things easy, what we do is we just combine the constants and we just say something like this. 1/2 y squared is equal to 1/2 x squared plus c. Now very often these differential equations come with some conditions. This would make it an initial condition problem. So let's say in this case we were told that y is equal to 2 when x is equal to 1. Well, what that allows us to do is plug in those values for x and y and solve for c. So we'll do that. 1/2 times 2 squared, or 4, is equal to 1/2 times 1 squared, or 1, plus c. And if we solve that for c, we get, let's see, 2 minus 1/2, or 1/2. So c is equal to 1 1/2. In addition to that, we typically will take our solution, which is 1/2 y squared is equal to 1/2 x squared plus c, and we'll plug our c value in. We'll call it 3/2, and we will solve that for y. So we'll multiply both sides by 2, get y squared is equal to x squared plus 3, and then we are going to take the square root of that. Y is equal, of both sides, is equal to plus or minus the square root of x squared plus 3. Well, here's where things get a little tricky. If you recall, we were told y is equal to 2 when x is equal to 1. And if you were to plug 1 in for x, you would have the square root of 4, which, or you'd have plus or minus the square root of 4, which would be positive 2 or negative 2. But because y has to be positive 2 when x is equal to 1, our final solution can only be the positive root, y is equal to x squared plus 3. And as you know, the domain of that function would be all real numbers from negative infinity to positive infinity, because no matter what we put in for x, when we square it, it's going to be positive or 0, and when we add 3 to it, it's going to be positive. So we end up with a domain of negative infinity to positive infinity. So let's try another problem like that. Dy dx is equal to negative 2xy squared, and y is equal to 1/4 when x is equal to 1. All right, so the first thing we want to do is separate the x's and the y's. And if you do that, you're going to get dy over y squared is equal to negative 2x dx. The negative can go on either side. So if I were going to write this out to make it easy for me to integrate, I would write y to the negative 2 dy is equal to negative 2x dx, and then integrate both sides of that. And when I integrate both sides of that, I would get y to the negative 1, with a negative 1 out front, is equal to negative 2 times 1/2 times x squared plus the constant on the right-hand side. And you can verify that's correct. If you differentiate both sides of that, you'll get back to y to the negative 2 on the left-hand side and negative 2x on the right-hand side. At this point, we need to plug in x and y and solve for the constant c. So negative 1 times 1 over 1/4, which is going to be 4, is equal to negative 2 times 1/2. Those cancel out, but we still have a negative there, times 1 plus c. So we have negative 4 plus 1, or negative 3, is equal to c. Okay, so where does that leave us? That leaves us here. We have negative 1 y to the negative 1 is equal to the opposite of x squared minus 3. We're going to go ahead and solve this for y. We'll multiply both sides by negative 1 and write this as 1 over y is equal to x squared plus 3. So y would be equal to 1 over x squared plus 3. And I think it's a good idea to check and make sure that you meet the conditions that y is 1/4 when x is equal to 1. And if you plug that in, that is the case. And sometimes you're asked about the domain of this function. So our domain, as you can tell by looking at it, is from negative infinity to positive infinity, because there are no restrictions on the value of x. All right, and before we finish, we're going to do one more of these, a little bit more challenging. So here's our situation. This time we have dy dx is equal to xy quantity squared. And remember, these are separable differential equations. So I think the best thing to do first would be to distribute that exponent and write this as dy dx equals x squared y squared. And now separate the variables, so you'll have dy over x squared is equal to x squared dx, which I would write as x to the, sorry, I wrote x, I meant y squared in the denominator here. And I would write that as y to the negative 2 dy is equal to x squared dx to make that easier for me to integrate. So when we integrate that, we're going to find the antiderivative. So what do we have? We have y to the negative 1, but we need a negative 1 out front of that, is equal to 1/3 x cubed plus c. Now, we have some initial conditions that I didn't originally state, and those initial conditions are x is equal to 1 when y is equal to 1. So we're going to plug those in and solve for our constant. So negative 1 is equal to 1/3 times 1 plus c. So when we go ahead and we solve that, we have c is equal to negative 1 minus 1/3, or negative 4/3. So when we go back to solve find y from our solution, we have negative 1 y to the negative 1 is equal to 1/3 x cubed minus 4/3. And I would write this as 1 over y is equal to the opposite, distribute the negative on the right-hand side, 1/3 x cubed plus 4/3, and therefore y is going to be equal to the reciprocal of that. Well, to make that easier, I might write that as the following before I take the reciprocal. The opposite of x cubed plus 4 over 3 because we have a common denominator. So we're going to take the reciprocal of that to solve for y. So we have negative 3, if we want to put that in the numerator, over x cubed minus 4. All right, and we have to think about the domain here. We have no restrictions for the numerator, but we know that x cubed minus 4 cannot be equal to 0. So x cubed cannot be equal to 4, which means that x cannot be equal to the cubed root of 4. So as you recall from discussions about rational functions in pre-calc, this function has a vertical asymptote where x cubed minus 4 is equal to 0. In other words, the function doesn't exist there. And so what we're going to do is we're going to take a look at the graph of this function, because remember, we need the part of the curve that not only solves the differential equation, but it also meets these conditions that when x is equal to 1, y is equal to 1. So here's a graph of that function on our calculator, and that vertical asymptote occurs at the cube root of 4, because that makes the denominator 0, which happens to be about 1.6. Now remember, our initial condition was we needed x to be 1 when y is equal to 1. So we have to decide which part of this curve that we need to use, and obviously we are going to use the left-hand side of the curve when x is equal to 1, y is equal to 1. So the domain for the part of the curve that we are interested in is the following: from negative infinity to the cube root of 4. So to be clear, we need the continuous part of the function that we solve for that contains the point 1, 1, and that is on this interval right here.